Okay, Chemistry 111. This is Chapter 9, which deals with chemical bonding and the basic concepts surrounding chemical bonding. And in order for us to really get started in talking about bonds that occur in chemicals, we have to look at electrons first. And the good news is that we spent a lot of time talking about valence electrons earlier on in the last two chapters. We talked about electron configuration and principal quantum numbers, things like that. And so you should be aware that valence electrons are the outer shell electrons of an atom. The valence electrons are the electrons that participate in chemical bonding. So the reason why valence electrons are going to be so crucial in this chapter is because those are the electrons that participate in bonding. And so when we're studying chemical bonding in Chemistry 111, we're mostly going to be focusing on main group elements, right? If you remember main group elements, these were the group A elements, okay? So group A. Okay, so basically that means the S block, and the P block, right? We're not going to be looking at lanthanides and actinides or the transition metals very much. Now, if you remember the alkali metals in the alkaline earths, group 1A and 2A, you probably remember that they have the same outer electron configuration, right? The elements that are in group 1A, like lithium, sodium, potassium, so on and so forth, they have one valence electron. The elements that are in group 2A, the alkaline earth, they have two valence electrons, right? Two valence electrons, and that is reflected by Ns2. If we look at, groups 3A, 4A, 5A, 6A, and 7A, we see that they have 3, 4, 5, 6, and 7 valence electrons, respectively. Let's take a look at the periodic table and look at these main groups, okay? So we have the main groups labeled. We have groups 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. And the way that we represent those valence electrons are to use what's called a Lewis dot symbol. So say, for example, we were looking at the Lewis dot symbol for lithium, okay? Here's lithium right here. It's element number 3. Now we know that lithium, right, has an electron configuration of helium and then 2s1. So it has one valence electron. So the number of valence electrons is also reflected in the group number, right? Okay, well, the way that we write a Lewis dot structure or a Lewis dot symbol for lithium is we simply write lithium and then we put a dot next to it like that. And if you're thinking, well, Mr. Dion, your dot is on the right and the dot here is on the left, that's not important. Okay, it doesn't matter where you put the dot. Okay, you're showing with this Lewis dot symbol that lithium has one valence electron. Say, for example, we had phosphorus. So I'm skipping all the way over to phosphorus, okay? Well, phosphorus is in group 5A. Remember that number, that 5 in the group 5A, reflects the number of valence electrons. So what do you do if you have more than 4 valence electrons? Let me show you. If you have 5 valence electrons, since there are 4 sides around the phosphorus atom, the way you do it is like this. You want to have the maximum number of unpaired electrons. So we go like this, 1, 2, 3, 4. Now we've got one electron on each of the 4 sides. Now we're going to have to pair up another electron. So 5, okay? Now I could have put that last electron, I could have put it here. That's fine. I could have put it here. That's fine as well. And I could have put it here. It doesn't matter where the electrons are. What matters is that you show that you have the maximum number of unpaired electrons, okay? And when you have to pair electrons up, well, you can put them on any side you want. Let's try another one. Say, for example, we have aluminum, okay? Aluminum is in group 3A. That means it's got 3 valence electrons. We would start by writing out the elemental symbol of aluminum, and we would put 1, 2, and 3. This is correct, okay? If you were to do this, if you were to say 1, 2, 3, and you pair up electrons like that, that's incorrect. Remember, you want to have the maximum number of unpaired electrons. So as the evening progresses, we're going to see more and more, or we're going to look at more and more Lewis dot symbols. So you'll get accustomed to using them, okay? I also want to point out that when you get all the way over to the noble gases in group 8A, Okay, with the exception of helium, they have 8 valence electrons. Look, we have 8 surrounding neon, 8 surrounding argon, so on and so forth. Okay, and when an element is going to participate in bonding, it has to have an unpaired electron. If you look at all of the other elements and you look at all of the Lewis dot symbols of all the elements here that I'm boxing in yellow, so that means everything except the noble gases, they all have a minimum of 1 unpaired electron. But the noble gases have no unpaired electrons. All of their electrons are paired up. And that is one of the reasons why noble gases don't participate in bonding. The first type of bond that we want to discuss is an ionic bond. Okay? And an ionic bond is an electrostatic force that holds ions together. Well, what's an ion? Well, remember that an ion can be either a cation, which is positively charged, or an anion, which is negatively charged. So say, for example, we want to make an ionic compound from lithium and fluorine. Well, first of all, how would I know that lithium and fluorine are going to form an ionic compound? The reason why I know that they're going to form an ionic compound is because lithium is a metal and fluorine is a nonmetal. So not only is the ionic bond formed by an electrostatic force that holds ions together, we know that we're going to form ionic compounds when we're dealing with a metal and a nonmetal. Again, lithium is a metal. It's on the left side of the metalloid line, and fluorine is a nonmetal. Well, what do we know about metals? We know that metals like to lose electrons. What do we know about nonmetals? We know that nonmetals oftentimes like to gain electrons. If we go back and look at our periodic table for a second, if we just think about those two elements, lithium and fluorine, what's the closest noble gas to lithium? The closest noble gas is helium. Helium only has 2 valence electrons, right? So how, or two electrons total, how would lithium become isoelectronic with helium? It has to lose 1 electron, right? If it loses 1 electron, it becomes isoelectronic with a noble gas. Fluorine is closer to neon than any other noble gas. So if fluorine gains 1 electron, it becomes isoelectronic with a noble gas. So that's why lithium wants to form a lithium cation, and that's why fluorine wants to form a fluoride anion. Here's the electron configuration of lithium, 1s2, 2s1. If it loses 1 valence electron, looky, it becomes isoelectronic with what? Helium, which has an electron configuration of 1s2. The electron configuration of fluorine is shown here, 1s2, 2s2, 2p5. If the fluorine gains that 1 electron, then it has an electron configuration of 1s2, 2s2, 2p6, which is isoelectronic with neon. So you can see that everybody's happy. Both elements, when they're converted into their ions, are going to be isoelectronic with noble gases. Now what do we have? We have something with a positive charge and we have something with a negative charge. And so they are going to be attracted to each other. And that electrostatic force that holds the positive charge of the cation to the negative charge of the anion is the ionic bond. Down here, I have an equation showing lithium losing an electron, and I have another equation showing fluorine gaining an electron to form fluoride. This should say F minus. If you tally up those two equations, what do you get? What's the same on opposite sides is the electron. So you can see that overall, this is my net equation. The lithium cation plus the fluoride anion gives us lithium fluoride. Ionic compounds like lithium fluoride are solids, right? The electrostatic interaction that holds those ions together is very strong, and it's so strong that we end up with solid compounds with high melting points and high boiling points. Let's try an example. Example 9.1 says use Lewis dot symbols to show the formation of aluminum oxide, Al2O3. Now we've already covered nomenclature, and so you know how to name this compound, and you know how to put the formula together. Aluminum oxide is found in the mineral corundum. Ruby and sapphire are varieties of corundum. Well, let's kind of make this as simple as we can. In Al2O3, I have 2 aluminum atoms, don't I? If I just think about the Lewis structure of my 2 aluminums, since aluminum is in group 3A, it's going to have 3 valence electrons. 1, 2, 3. 1, 2, 3. So that's my 2 aluminum atoms. I've got 3 oxygen atoms. Oxygen is from group 6A. So if I write down 3 oxygens, 1, 2, 3, it's got 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. There's my 3 oxygens. Each one has 6 valence electrons. Well, in order for the oxygens to gain enough electrons to become isoelectronic with the nearest noble gas, how many electrons would they have to gain? Let's take a look back here. Here's oxygen on the periodic table. It has to gain 1, 2 electrons to become isoelectronic with neon, the nearest noble gas. Well, if I have 3 oxygens and each one of them has 6 valence electrons and they all need a total of 8, that means that each one needs 2. 3 times 2 is a total of 6. Look what I have here. I have 3 valence electrons here and 3 valence electrons here. So what's going to happen is that those aluminums are going to transfer all 6 of those valence electrons to the oxygen. So what will I be left over with? I'll be left over with 2 aluminum 3+ cations, and I'll be left over with oxygen. They'll all have 8 valence electrons, but remember that oxygen only has 6 valence electrons. So if it's got 2 extra electrons, that means that each one of these is going to have a 2- charge. Look at this. What's the total positive charges I have? 2 times positive 3. That gives me a total of positive 6 right here. What's the total charge of my oxide? -2 plus -2 plus -2. That gives me a total charge of -6. And so we've represented using Lewis dot symbols how we combine 2 aluminum cations plus 3 oxide anions to produce Al2O3. Now, again, this is going to be a solid, as you can clearly see. Al2O3 is a solid. This might be a little bit different than the way the book solved it, but I think it makes it abundantly clear what is happening here. Give me a thumbs up if you follow me on this. The formation of an ionic compound from a metal who loses electrons and a non-metal who gains electrons. All right. Well, we saw that lithium fluoride in the previous slide. We saw that lithium fluoride was a solid. Aluminum oxide is a solid. If you're thinking about other ionic compounds that you know from your daily life, like sodium chloride, that's also a solid. What is it that's holding these ions together? We said it was an electrostatic force. Well, is the electrostatic force that holds some ionic compounds together stronger than other ionic compounds? The answer is yes. The electrostatic force that holds anions and cations together, we call this lattice energy. And the lattice energy, which is defined as U in our textbook, is the energy required to completely separate 1 mole of solid ionic compound into gaseous ions. Okay, that would be akin to doing this. If you had sodium chloride, which is a solid ionic compound, if you could measure the amount of energy required to convert both of those into their ions in the gaseous phase, okay, that would be equal to the lattice energy. Okay, if you could measure how much energy that would require, that's the lattice energy. Now, lattice energy U, we can, in some books they use E. as the variable. So we can say here lattice energy is equal to E, which is the potential energy of those ions that are held together. Well, what's it equal to? It's equal to a constant K. That's not important for us right now. What's important is that the lattice energy is equal to the product of the charges of the cation and the anion divided by the distance between the ions. If the charge of the cation and anion are on the numerator, or in the numerator, what does that tell us? It tells us that the greater the charge, the greater the lattice energy. Lattice energy increases as Q increases. If our R, our distance between our ions, is in the denominator, what does that tell us? The smaller R is, the greater the lattice energy will be. As R decreases, lattice energy is going to increase. Let's take a look at some comparisons here. If we compare magnesium fluoride to magnesium oxide, the charge of magnesium in both of these is +2, isn't it? But the charge of fluoride is -1, and the charge of oxide, as we just saw, is -2. That means when you plug these numbers, okay, whether you're looking at magnesium fluoride or magnesium oxide, you see that the numerator is going to give you a very different product, right? The product of the numerator here would be -2, and the product of the numerator for magnesium oxide would be -4. -4 is a much bigger number, isn't it? It's twice as much. So that's why the lattice energy for magnesium oxide is going to be higher than that for magnesium fluoride. You can see that right here. Now, if you're thinking, well, it's not double, okay, it's 1,000 kilojoules per mole more roughly, but it's not double, Mr. Dion. Well, remember, it doesn't solely depend on the charges of the cation and anion. It also depends on the distance between the ions. So we have to evaluate both of those when lattice energy is measured. Let's look at another example before we move on to the next slide. What if we compared lithium fluoride and lithium chloride? Well, lithium has a charge of +1, fluoride has a charge of -1, and chloride has a charge of -1. So that means Q plus times Q negative, the charge on the cation times the charge of the anion, is going to be the same, whether it's lithium fluoride or lithium chloride. Well, then why is the lattice energy of lithium chloride greater than that of why is the lattice energy lower? Well, remember that as we go down a group, and the halogens go fluorine, chlorine, bromine, and iodine, what happens to this atomic size as we go down a group? Size increases. So if chloride is larger than fluoride, that means you're going to have a bigger number in the denominator, which is going to result in a smaller lattice energy. Give me a thumbs up if those two concepts make sense to you. Lattice energy is proportional to the product of charges divided by the distance between the ions, or R. Great. Let's take a little bit of a more detailed look at this concept of lattice energy. All right? Let's review it one more time. It says that lattice energy is the energy that it would take to take 1 mole of a solid ionic compound and separate it into its gaseous ions. That's really important. It's going to be ions in the gas phase. Well, since delta H is a state function, we can, even if we can't measure our lattice energy directly, we can measure it indirectly. Let me show you what I mean. This is the Bourne-Haber cycle for determining lattice energy. You can see again that the lattice energy is the amount of heat that it would take to convert 1 mole of a solid substance into its gaseous ions that are shown here. Now you notice that it says negative of lattice energy here. Why? Because my arrow is going in this direction, but the arrow on the slide is going in this direction. Let me start with the two elements in their standard states and see if you can follow me here. Okay, if I start with solid lithium and gaseous fluorine in a balanced equation, okay, if I combine those, okay, the amount of heat that's given off is negative 594 kilojoules. All right. Well, what if I wanted to convert those two elements, from their standard states into gaseous ions? Well, since lithium is a solid, I would have to convert it to a gas. What's that process called? It's sublimation. It's going to take heat energy to do that. It takes 155 kilojoules to do that. Now I've got lithium in the gaseous phase. What if I want to remove an electron? Well, that's defined as ionization energy, isn't it? The removal of 1 mole of electrons from 1 mole of an element in the gaseous phase. Here's the ionization energy. Now we have the lithium cation in the gaseous phase. Now what about my fluorine? Well, you remember that fluorine is a diatomic element. It's F2. So if I want to have just fluoride in the gaseous phase, that means I'm going to have to break those two fluorines apart. That's the delta H of dissociation, of breaking the fluorine-fluorine bond. That's going to require energy. Then there's a certain amount of energy associated with the electron affinity. Since fluorine has a high electron affinity, it's going to want that electron. And so we have negative 328 kilojoules for our electron affinity. Now, when I take those two gaseous ions and I combine them to get the solid compound, that's the negative of the lattice energy, isn't it? Because lattice energy is going this way, right? Okay. Well, based off of my delta H overall, right here, if I know that, and I know my delta H of sublimation, delta H of dissociation, my ionization energy of my lithium, and my electron affinity, that means I'd have delta H1, delta H2, delta H3, delta H4. I could solve for delta H5, couldn't I? Of course I could. We're going to look at an example later on where we apply the Bourne-Haber cycle for determining lattice energy. Before we do that, let's look at some lattice energies for some metal, halides, and oxides. All you need to know about this table is the trends. Okay, that's what's important here, are trends. Let's compare lithium fluoride, chloride, bromide, and iodide. There's a little subscript here that shouldn't be here. Anyhow, so we go from fluorine to chlorine to bromine to iodine. What do we know? Size increases as we go down a group, doesn't it? Now, the lithium is not changing. The charge isn't changing either because the halogens are all going to take on a -1 charge. But you see that the lattice energy decreases as we go from fluoride to chloride to bromide to iodide. Let's think back to our equation. That lattice energy, let me just write it like this. Lattice energy, or U, is going to be proportional to product of the charges divided by the distance between the elements. Well, this is going to remain a constant going from fluoride to chloride to bromide to iodide with my lithium. But what changes? R is going to change, doesn't it? R is going to get bigger and bigger and bigger. And as R increases, U is going to decrease because they're inversely proportional. We see the exact same trend when we go from sodium chloride to bromide to iodide. We see the same trend when we go from potassium chloride to bromide to iodide. Exact same trends. We see that the lattice energy decreases here, and it decreases here for the exact same reason. Let's take a look at another one. If we compare sodium oxide and magnesium oxide, the last two. Well, why would the lattice energy of magnesium oxide be so much higher than that of sodium oxide? Again, sodium has a charge of +1, but magnesium has a charge of +2, so it's got double the amount of charge. All right. Even though sodium is smaller, it's a double whammy here because sodium has a lower charge and it's also bigger. So it's going to have a lower lattice energy. Anyhow, I'm kind of just rehashing the same point over and over here. So why don't we just move on from ionic bonds and get into what the major portion of this chapter is about, and that is covalent bonds. Okay, the major part of this chapter is about covalent bonds. So we've discussed ionic bonds. Ionic bonds are an electrostatic force between a metal cation and a non-metal anion. That's all we've talked about this evening, are ionic bonds. Covalent bonds, again, major topic of this chapter. A covalent bond is a chemical bond in which two or more electrons are shared by two atoms. And those two atoms are both going to be nonmetals. Both are nonmetals. If we think about the ionic bond again, the electrons are being transferred from the metal to the nonmetal, right? Transferred. Whereas in the covalent bond, we're going to see that the electrons are going to be shared by two atoms. Let's take a look at an example. Why would two atoms share electrons? What would they have to gain? Well, if you share something with somebody, it's like you both are partaking of its goodness, so to speak, okay? Look at fluorine. The fluorine element has 7 valence electrons, right? Because fluorine is in group 7A. So this would be its Lewis dot structure, 1, 2, 3, 4, 5, 6, 7. It's got 1 unpaired electron. It's not isoelectronic with a noble gas, is it? How many electrons does fluorine have to gain to become isoelectronic with a noble gas? Here's fluorine. It has to gain 1 electron to become isoelectronic with neon. So if I have 2 fluorines and they approach each other, they get close enough with each other, you see how this kind of looks like a Venn diagram here? Well, if you look at the original circle that was around the fluorine, there was only 7 electrons in there, wasn't there? But when the 2 atoms approach each other, look how many electrons are in this circle now. There's 8 electrons in the circle for the fluorine on the left, and there's 8 electrons here. The 2 electrons in the middle, right, these 2 electrons here, these are being shared. So it's as if they're both partaking of those electrons. So now it's as if both of them are isoelectronic with a noble gas by sharing those electrons. Okay, now how do we represent that? Well, instead of always drawing this kind of Venn diagram looking thing here, a better way to do that is to show that when the 2 fluorines approach each other, right, they're going to share the 2 electrons in the middle. Okay, the electrons that I'm highlighting, these are the shared electrons. Instead of writing them as 2 dots, we write them as a single dash or a single line in between. Okay, and when we have a line like that, we know that that line signifies that there are 2 electrons in there. So it's as if the fluorine on the left has 1, 2, 3, 4, 5, 6, 7, 8 electrons. Hey, it's isoelectronic with neon. It's as if the fluorine on the right has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Now it's isoelectronic with neon. We are never going to draw Lewis structures, what are called Lewis structures, like this. Okay, it's not incorrect, but we're never going to draw them like that. Whenever 2 elements are sharing electrons, we're going to draw a bond. Okay, so this is a bond right here. We'll draw a single line connecting them, and we know that in that bond there are 2 electrons. Let's talk about how we would draw a structure that shows the sharing of electrons in water. Okay, a molecule we are all very familiar with. Everybody knows the molecular formula of water, H2O. It means it's got 2 hydrogens and 1 oxygen. What was the Lewis dot symbol for hydrogen? Since hydrogen is in group 1A, it has one valence electron. And there's two hydrogens, aren't there? What about oxygen? Oxygen was in group 6A, and so oxygen had 1, 2, 3, 4, 5, 6. Now, if you're wondering, why did I start pairing them up? Well, that's because of experience. If you're not used to this, what you can do is this. You'd say 1, 2, 3, 4, and then you start pairing them up, 5, 6. Now, another nuance, if you're wondering, like, hey, Mr. Dion, when you're pairing them up, why don't you go 5, 6 like this and put the paired electrons close to each other? The reason why is because electrons want to repel each other. They want to get as far away from each other as possible. So the way that I would draw my Lewis structure of oxygen, I would just say 1, 2, 3, 4, 5, 6, like that. Well, we looked at this earlier. We said that oxygen needs to gain 2 electrons in order to become isoelectronic with a noble gas, neon. Looky, looky, we just happen to have one valence electron from hydrogen and one valence electron from another hydrogen. Remember that since hydrogen is in the first period, it's never going to be surrounded by 8 electrons like the rest of the noble gases, right? What's the noble gas that's closest to hydrogen? It's helium. And helium has 2 paired electrons that are 1s2, like that. So that means that hydrogen only needs 1 more electron to have 2 shared electrons, and then it will be as if it's isoelectronic with neon. What if I organized my atoms like this? I put my oxygen like this, I put my hydrogen here, and my hydrogen like this. It's like solving a puzzle. If I was to bring those 2 hydrogens even closer together, okay, what would it look like? It would look like this. Now what do we see? We see that the oxygen is surrounded by 1, 2, 3, 4, 5, 6, 7, 8 electrons. Now it's as if it's isoelectronic with neon. It's got 8 valence electrons. What about hydrogen? Hydrogen is only surrounded by these 2 electrons. The other hydrogen is surrounded by those 2 electrons. Remember, hydrogen only needs 2 electrons to be isoelectronic with a noble gas. Well, since this pair of electrons is shared and this pair of electrons is shared, we're going to draw an even more accurate representation, and we're going to say the hydrogen is connected to the oxygen with a bond, because a bond has 2 electrons. And then the other electrons are going to remain on the oxygen like this. When we have unpaired electrons on an atom, we call these lone pairs. So the oxygen in water has 2 bonds and 2 lone pairs. Each of the hydrogens in water has 1 bond. With that in mind, let's take a look at a couple other examples. Let's take a look at an example that has a double bond. If we think about CO2, that's carbon dioxide. Carbon is in group 4A. It's got 4 valence electrons, 1, 2, 3, 4. Oxygen, again, is in group 6A. It's got 1, 2, 3, 4. 1, 2, 3, 4, 5, 6 valence electrons. 1, 2, 3, 4, 5, 6 valence electrons, like that. How am I going to organize these so that both of these, or all 3 of these elements, become isoelectronic with a noble gas? Well, it actually takes some fiddling. And if you're wondering, like, hey, Mr. Dion, how do you actually put these structures together? The answer is T&E, trial and error, right? You're going to have to work at it. You're going to have to practice it. And the more you practice, the more proficient you will become. If we were to draw one of the oxygens like this, sorry, Mr. Dion needs a new prescription pretty bad. Anyhow, and we were to draw a carbon like this and put another oxygen like this. Well, we could show the sharing of these 2 electrons and the sharing of these 2 electrons, couldn't we? We could connect them with a bond. Then we'd have something that looks like this. If you look at the 2 oxygens in here, they're actually quite content. They're both isoelectronic with a noble gas. Let me prove it to you. They both have 1, 2, 3, 4 5, 6, and 7, 8 valence electrons. So they're both isoelectronic with neon. But what about the carbon? Is it isoelectronic with a noble gas the way it is here? The answer is no. It's surrounded by 1, 2, 3, 4, 5, 6 valence electrons. How am I going to get that carbon enough electrons? The answer is this. I'm going to take these 2 electrons and I'm going to make another bond. I'm going to take these 2 electrons and I'm going to make another bond. Now you see that we have 2 double bonds. Are all 4 elements in here isoelectronic with a noble gas? You bet your bobby socks they are. Look at the oxygens. 1, 2, 3, 4. Every bond has 2 electrons. 5, 6, 7, 8. Look at the carbon. It's surrounded by 4 bonds. There's 2 electrons in each bond. 1, 2, 3, 4, 5, 6, 7, 8. So all of the elements in this structure, in this Lewis structure, are isoelectronic with the noble gas. So this is a perfectly correct Lewis structure. So there's a double bond. So now we've looked at single bonds, double bonds. Let's take a look at triple bonds. And there's a triple bond in a really abundant molecule on the planet Earth, and that's nitrogen. Remember that nitrogen is in group 5A. It's got a total of 1, 2, 3, 4, 5 valence electrons. If I have 2 nitrogens like this, and I'm going to go a little bit quicker this time, you're going to see that the only way that I can put these 2 atoms together and have them each be isoelectronic with the noble gas, neon, meaning that each are surrounded by a total of 8 electrons, is for me to pair up all of the electrons. I'd have to pair up these electrons, I have to pair up these electrons, and I have to pair up these electrons. Right? What would that mean? That would mean that each nitrogen would be left over with a lone pair, and I'd form 1, 2, 3 bonds. 1, 2, 3. Let's examine this. Each nitrogen now is surrounded by 1, 2, 3, 4, 5, 6, 7, 8 electrons. So it's both as if they are isoelectronic with a noble gas, and that is a perfectly good Lewis structure for N2. And here we have a triple bond. So now we've seen single bonds, double bonds, and triple bonds. In water, carbon dioxide, and nitrogen. Give me a thumbs up if you follow me on the concept of single bond, double bond, and triple bond, and the sharing of electrons in bonds, so that the elements in these covalent compounds attain as if they had the electron configuration of a noble gas. All right, good. So I got Julius, Trevor, Chris, and Bruce that are with me. Okay, good. Well, let's go back to our slide deck. We were right around here. What's important is that you understand that covalent bonds, whether they are single, double bonds, or triple bonds, have an effect on bond length. That's summarized down here. A single bond is the longest, and a triple bond is the shortest. The reason why a triple bond is shorter than a double or a single is because every time you have electrons being shared between 2 atoms, the atoms have to get closer and closer in order for those electrons to be shared. Let's take a look at some examples here. If you compare a carbon oxygen, let's compare a carbon nitrogen. If you compare a carbon nitrogen single bond, double bond, and a triple bond, what do you see the effect is on bond length? As the number of bonds increases, the bond length decreases. You can see a similar trend between a nitrogen-oxygen single bond and double bond. What do you notice? As the number of bonds increase, the bond length decreases. We also see it right here for a carbon-carbon single, double, or a triple. Bond length decreases. This is a rule that you have to know. I've seen this rule asked several times on the final exam. Let's compare sodium chloride and carbon tetrachloride. Sodium chloride is an ionic compound because it's comprised of a metal and a nonmetal. And carbon tetrachloride is a covalent compound, meaning that it's only held together by covalent bonds because everything in here is a nonmetal. Carbon is not a metal and chlorine is not a metal. If you look at their appearances, the sodium chloride is ionic. It's a white solid. It's held together by those strong electrostatic forces between the cation and the anion, whereas carbon tetrachloride is a liquid. If you look at their melting points, you also see a big difference. Sodium chloride doesn't melt till 800 degrees Celsius, whereas carbon tetrachloride is a liquid at room temperature. It melts at minus 23. Other things that are interesting would be solubility in water. Ionic compounds are very soluble in water, whereas covalent compounds are not very soluble in water. What else do we see? The boiling point of an ionic compound is much higher. Why would that be? Because it takes a lot more energy for vaporization to occur in an ionic compound. Think about it. The electrostatic forces between a positive and negative charge are much stronger than the covalent bonds or the intermolecular forces that hold molecules of carbon tetrachloride together. So, in a nutshell, you should know that ionic compounds are normally solids at room temperature. Covalent compounds are oftentimes liquids or gases at room temperature. And if something's a solid at room temperature, it's generally speaking going to have a higher melting point, higher boiling point. Ionic compounds are also soluble in water, and covalent compounds are oftentimes not very soluble in water. Well, so far the only covalent bond that we looked at in detail in the slide deck was the fluorine bond, right? We drew this a little while back. But then we looked at the Lewis structure of water, which was H2O. We looked at the Lewis structure of carbon dioxide, CO2. Okay, and we looked at the Lewis structure of nitrogen, or N2. There's a big difference between fluorine and fluorine being bound together, or nitrogen and nitrogen being bound together, compared to, let's say, oxygen and hydrogen, or carbon and oxygen. Why? Because fluorine and fluorine, those are identical elements, aren't they? They both have the same propensity to pull electrons towards themselves. So they share perfectly equally. Same thing with the two nitrogens in N2 gas. They share electrons perfectly. But what I'm here to tell you is that when you have two elements that are different, like a hydrogen and an oxygen, or a carbon and an oxygen, and these are just some examples, they share the electrons, right? Because these are covalent compounds, right? There's no metals in water or carbon dioxide, so they must be covalent bonds, which means that the electrons are shared. But what we're going to see is that the electrons are not shared equally. Okay, there's unequal sharing of electrons, resulting in a polar covalent bond or a polar bond, which is a covalent bond with greater electron density around one of the two atoms. Here's an example. hydrogen fluoride. If you look at what's called an electrostatic potential map of hydrogen fluoride, this being the hydrogen, here's my bond, and this being the fluorine, the more red the electrostatic potential map is, it means greater electron density. So what you can see here in the electrostatic potential map is that there's a lot more electron density near the fluorine than there is near the hydrogen. In fact, the color blue means low electron density. Now, why would this be? Again, it's because the fluorine has a greater ability to pull electron density towards itself. Another way we could describe it is to say the hydrogen is electron poor and the fluorine is electron rich. We use the symbol delta to represent partial. So remember, even though the hydrogen is electron poor, it's not a cation. It's partially positive. So we write delta plus. Whereas the fluorine is not an anion, but it's got more of the electron density towards itself. And so we put it's partially negative, delta minus. The way you can describe a polar covalent bond is like this. My daughter is 5 years old. Her and I like to go to Costco sometimes, and we'll share a slice of pizza. Do we share the pizza? Do I share some with her? Absolutely, I do. But who do you think gets more pizza, a 5-year-old or dad? The answer is dad. We're still sharing, right? We're totally sharing it, but one of us is going to get more than the other. And that's essentially what a polar covalent bond is. These electrons are being shared, but more of those two electrons, more of the density of those electrons is going to be pulled towards one of the elements versus the other. Now you might be wondering, why would one element have a propensity to pull electron density towards itself? Well, that is what we call electronegativity. Electronegativity is the ability of an atom in a bond to attract electron density towards itself. Notice it says here in my notes, the ability of an atom to attract towards itself the electrons in a bond. So bonding is key here. You might remember that earlier on in this class, we discussed electron affinity. Electron affinity, this was for atoms. Okay, when we looked at electron affinity, that was dealing with atoms. And we said, okay, well, a chlorine, for example, it wants to gain an electron because then it becomes isoelectronic with a noble gas. Whereas electronegativity deals with elements that are in bonds. The most electronegative element, in fact, is fluorine, most electronegative element on the periodic table. And it has been assigned a value of 4.0. If you're wondering, Mr. Dion, did you just pull that, number out of thin air? The answer is no. Here are the electronegativity values for common elements. Let's take a look. Again, fluorine is the most electronegative element on the periodic table. It's got a value of 4.0. Cesium and francium, these are about the least electronegative elements on the periodic table. They're around 0.7. Well, what do you notice here? You can see that as we go across a period, going from, say, lithium to beryllium to boron to carbon to nitrogen to oxygen to fluorine, what do you see? We go from 1.0 to 1.5 to 2 to 2.5 to 3 to 3.5 all the way up to 4. So what's the net result? Is that as we go across a period from left to right, we get increasing electronegativity. What else? Let's look at a group. If you look at group 1A, generally speaking, if you start at lithium and you go down like this, generally speaking, you see that electronegativity decreases. Look, if you look at another example, let's say we look at group 5A. You see that generally speaking, going down the group, electronegativity decreases. So we could say that going from the bottom to the top of a group, we get increasing electronegativity. So we can put here from bottom to top of group or family. What else do we see here? We see that the electronegativities of nonmetals are generally much higher than that of those of metals. And you see that the metalloids are kind of somewhere in between. Well, what conclusion could you draw from looking at these numbers? The conclusion that I would make is this. The two types of bonding that we've looked at this evening are ionic and covalent. Now, ionic bonding occurred between a metal and a nonmetal. So that means that the difference in electronegativity and difference in I write that as delta En. The difference in electronegativity for ionic compounds is going to be higher than that of covalent compounds, isn't it? Because we're going to have a greater disparity in electronegativity, let's say between metals and nonmetals compared to nonmetals and metals. We're going to see several examples of this along the way. Now, if you're the kind of person who needs to see a graph for everything, here's the trend in electronegativities that we saw on the periodic table in the previous slide. Say, for example, if you just look at period 2. So this is the second period. What's the trend? As we go from lithium across to fluorine, we see that electronegativity increases. Same thing for the second period. Now, when we get to the third period, things get a little bit more interesting because we have the transition metals. But all I need you to know is the general trend, and that is for main group elements, electronegativity increases going across a period. Same thing is true in the fourth period. Don't worry about the anomalies for the transition metals. Now, is there a way that I can quantify the difference in electronegativities using that periodic table that we saw a couple of slides ago and determine whether something is ionic or covalent? Well, the answer is we kind of have three range areas, so to speak. If I calculate the delta En as being the absolute value of the difference between the two elements in my bond, so A minus B, whether it's two nonmetals or a metal and nonmetal, if I calculate the absolute difference between the two elements in the bond, if the difference is less than 0.4, then you're dealing with pretty much an equal sharing of electrons, and we say that the bond is purely covalent. Whereas once we get above 0.4 and below 2, we say that the bond is covalent, but we say it's polar covalent. What does polar mean? Polar, remember, was when we have an unequal sharing of electrons. It's when we have a bond between two elements of differing electronegativities. So again, if the difference in electronegativities between those elements falls in that magic area between 0.4 and 2, we say the bond isn't covalent and it's not ionic. It's polar covalent. The electrons are being shared, but they're being shared unequally. Finally, if I have a difference of electronegativities that's greater than or equal to 2, I say in that case, the difference is so great that the bond is ionic. You got to know the difference between covalent, polar covalent, and ionic bonds. Let's review. Covalent bonds, this is where electrons are shared, completely shared. Whereas in ionic bonds, electrons are transferred, aren't they? They're transferred from a cation to an anion. An example of a compound that's purely covalent would be something like N2. Of course, the two elements are going to share their electrons perfectly, because if I have two nitrogen atoms, they both have the same electronegativity. they both have a value of 3. What would be the difference in electronegativity for N2? It would be 3 minus 3, which equals 0. What about an ionic compound? An example of an ionic compound would be, let's say, lithium fluoride. Right? That's something that we looked at this evening. What's the difference in electronegativity between lithium and fluorine? Well, fluorine has a value of 4.0 and lithium has a value of 1. Let's do the math. The delta En is going to be 4 minus 1, which is equal to 3. 3 is greater than 2, and so lithium fluoride is held together by an ionic bond. Let's look at another example of something that's polar covalent, where we have a partial transfer of electrons. Let's go back to water, because there's 2 bonds in water, and they're both identical, right? They're both oxygen-hydrogen bonds. What's the difference in electronegativity between oxygen and hydrogen? Without going back to the periodic table, I have these memorized. Oxygen has an electronegativity of 3.5, and hydrogen has an electronegativity of 2.1. If I calculate the difference, I get 1.4. That falls in the range of 0.4 to 2. Therefore, the oxygen-hydrogen bond is a covalent bond, but it's a polar covalent bond. All right, with that information in mind, let's try a problem that I think is pretty reasonable. Question 9.2 says, classify the following bonds as being ionic, polar covalent, or covalent. Remember, our delta En is equal to the absolute value of the difference between the 2 elements, A and B, in our bond. Let's look at HCl. The delta En of HCl, in order to calculate that, we need the electronegativity of both hydrogen and chlorine. Now, you might have to look at the periodic table. I've gone ahead and written them down. Some of them I have memorized. Hydrogen has a value of 2.1, and chlorine has a value of 3.0. Let's do the math. 3.0 subtract 2.1. Instead of using the absolute value, I always just put the bigger number first, and I end up with a value of 0.9. That falls in between the range of 0.4 and 2. Therefore, this is a polar covalent bond. What about potassium fluoride? Potassium has an electronegativity of 0.8, and fluorine is 4.0. That gives me a value of 3.2, which is definitely more than 2, and so this would be an ionic bond that holds potassium and fluorine together. Finally, if we look at the carbon-carbon bond in this molecule, this is ethane. Well, my delta En, carbon has an electronegativity of 2.5, and the other carbon has an electronegativity of 2.5. 2.5 minus 2.5 is 0. This is a purely covalent bond. Give me a thumbs up if you follow me on that concept, and if you wish the entire next exam was just this problem. Calculate, determine whether this is a ionic or covalent or polar covalent bond. Good. All right. Well, if you remember on our blank page that we looked at a little while ago, I drew some Lewis structures, or what I called Lewis structures, of H2O, carbon dioxide, and nitrogen. Now, there's more method to this than just trial and error. There are actually some rules that you can follow to write Lewis structures. They are summarized on this slide. Writing Lewis structures. The first thing you're going to do is draw the skeletal structure of the compound, showing what atoms are bonded to each other. Normally, and this is not all the time, but most of the time, we put the least electronegative element in the center. Again, not always, but a lot of the time we do. Next, we're going to count the total number of valence electrons. How do we do that? We look at group number of each element. If we have a negative charge, we add 1 to our total number of valence electrons. If we have a positive charge, we're going to subtract 1. Next, you want to complete an octet for all atoms except hydrogen. Hydrogen, in order to be isoelectronic with helium, only needs 2 electrons. So hydrogen actually has a duet. Okay, I'm not making that up. And when the other elements become isoelectronic with a noble gas, they're surrounded by 8 valence electrons. That's called an octet. 8 valence electrons. The duet is 2 valence electrons. Okay, so what does that tell you? It tells you that when you have a hydrogen in any bond, hydrogen can only ever have one bond. Only. If you ever end up with a Lewis structure where hydrogen has 2 bonds, it feels bad to even write that. Okay, it's impossible. If the structure contains too many electrons, what you're going to do is you're going to play with it using trial and error, and you're going to form double or triple bonds as necessary in order for all the elements to have a complete octet. Another rule that I can tell you that's not on here is that whenever you have a fluorine, okay, fluorine always forms 1 bond and has 3 lone pairs. Okay, the other halogens, chlorine, bromine, and iodine, usually, not always, but usually have 1 bond and 3 lone pairs. Okay, not always. Fluorine, it's all the time. The other halogens, usually. Are there exceptions? C. Yes. With that in mind, let's try a problem. Here it says, write the Lewis structure for nitrogen trifluoride in which all 3 fluorine atoms are bonded to the nitrogen. If we examine this molecular formula, NF3, and we think about the rules that were on the previous slide, it said to put the least electronegative element in the center. Well, we know that fluorine is the most electronegative element in the periodic table. So that means that the nitrogen is going to be in the center, and it's going to be bound to 1, 2, 3 fluorines, like this. Now I'm going to erase all that, because where I always start when I'm doing a Lewis structure is here. The first thing I always do is tally up the number of valence electrons. Who could answer this for me? How many total valence electrons does nitrogen, the atom nitrogen, have? You might need a periodic table to answer this question. How many valence electrons does nitrogen have? It's not a trick question. Mr. Dion is not exactly. You're all right. It's 5. How many valence electrons does fluorine have? Well, fluorine is in group 7A. So that means it's got a total of 7 valence electrons. And how many fluorines do I have? I have 3. So I'm going to multiply that total number of valence electrons for fluorine times 3. That gives me 21 plus 5. That gives me a total of 26 electrons. That means that when I'm done my Lewis structure, it's got to have a total of 26 electrons. Now let's go back to where we were. Nitrogen is our central atom because it's the least electronegative, connected to 1, 2, 3 fluorines like that. Can anybody answer this question for me? How many electrons have I used up so far in what I've drawn? And it's not a trick. Yes. Trevor and Bruce both answered 6, and they're both correct. There's 2 electrons here, 2 electrons here, and 2 electrons here. 2 times 3 is 6. So if I take 26 and I subtract 6 from it, that means I got 20 electrons left to go. What did I tell you on the last slide? I said that fluorine always forms 1 bond. It has 3 lone pairs. That means I can fill up all of these fluorines with 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. That's a lot of electrons. How many have I used up? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I've used up a total of 24 of my 26 electrons. Do the 3 fluorines have complete octets? Absolutely they do. Just examine even one of them. It's surrounded by 1, 2, 3, 4, 5, 6, 7, 8 electrons. Now let me ask you one more question. Does the nitrogen have a complete octet? The answer is no. It's surrounded by 1, 2, 3, 4, 5, 6, but it's missing 2 electrons. Well, if I've used up 24 electrons and I have a total of 26, the last 2 electrons are going to go on the nitrogen like this. Now the nitrogen is surrounded by 1, 2, 3, 4, 5, 6, 7, 8. So the nitrogen has a complete octet. All of the elements have a complete octet. All of the electrons are accounted for. And my least electronegative element is in the center. This is a perfect Lewis structure. Nothing wrong with that. Next example says draw a Lewis structure for nitric acid, HNO3, in which 3 oxygen atoms are bonded to the central nitrogen atom, and the ionizable hydrogen atom is bonded to one of the oxygens. This gives us a lot of information here. And the reason why they provide so much information is because we're just learning the concept. What we're going to do now is take a 5-minute break. And during that time, I want you to, of course, take a short break, but I want you to try this problem on your own. And when we come back, we're going to take a look at it.